Good. So I will talk about TensorFlow now. So basically, same thing. I will keep a few things shorter to avoid a lot of repetition. So basically, why isn't that working? So basically, I will talk about a small overview about TensorFlow. I will not go too much into detail because it's pretty similar to PyTorch, although there are some key differences. I will talk about distributed deep learning with TensorFlow. We will have a short look at parallelism again, but I will keep that short because we already heard that from Fabian. I will talk about the different ways and scenarios that we have seen before and which solution or strategy in TensorFlow terminology is the most fitting. And I will talk about Horovod, which is an not extension, but a third-party tool to facilitate distributed deep learning on top of TensorFlow and other solutions. In the end, I will also show how to use that on our system. So basically, there are two main ways to use that right now. So there are containers and virtual environments. And I also will show a few examples. So basically putting it all together from resource allocation, MPI, multiple nodes, multiple processes, and containers. Good. So TensorFlow. TensorFlow typically does not come alone. So if you program pure TensorFlow, you're really, really low level. So most of the time, if you use TensorFlow, you use Keras, which is basically a higher level abstraction that allows you to define your models, your data sets, and so on a little bit more easily. So we see here on the right-hand side a very small, very basic example that I will also use on the remaining slides to show you the concepts and how that is done. Here we see the sequential API. So basically TensorFlow has a different APIs. So the sequential as well as functional API to define your model. Sequential is basically one layer after the other. And functionally, you can basically, you have a little bit more freedom how your network is actually put together. For example, you can connect one layer to a different layer that is, I don't know, 5 steps ahead or something like that. So you can do multiple cross-references with the functional API. So TensorFlow and Keras, they have some predefined models, for example, ResNets or stuff like that, that you can freely load and use without taking care of creating the model yourself or looking that up in related work. And there's also quite extensive documentation, sometimes not 100% clear all the time, because stuff is documented on different sites. So it's always the matter of finding the right information for you. But there's quite some documentation and tutorials available. Good. TensorFlow, we see that here on the right-hand side, the very basic process. It's pretty similar, but there are a few differences compared to PyTorch. So first of all, of course, you need some data that you want to process. This is a very simple example with an MNIST data set. So there is this predefined data sets collection where I can basically use MNIST, load the data, create a so-called data set that we can later use in the training process. Of course, I need a model. So here we have a very simple sequential model consisting of different layers. And in the end, we have a softmax activation to basically predict one of the 10 classes that the MNIST data set should basically predict. We compile the model in TensorFlow once, and then we can use it. And here, the using it is much shorter than in PyTorch. Yeah? It has advantages and disadvantages. You don't need to take care about implementing the manual training loop. However, it's kind of a black box. Yeah? So everything that is happening in FIT is not always that clear, and there are ways to intercept certain things, but yeah, a lot of stuff is abstracted from the user, so the user does not have to take care, and it can be good and it can also be bad in certain cases. So pros and cons. No manual training loop. That is partially a good thing, sometimes also a little bit tricky if you want to do some more complex stuff. There's in principle a large community, although we see a lot of people moving from TensorFlow and going to PyTorch because of reasons. Speed, so I put a question mark behind that because in recent years we have seen cases where TensorFlow is much more performant than PyTorch, but yeah, it's shifting. Yeah? So we also see cases where PyTorch is now much more performant than TensorFlow. In the past, speed was a thing. Currently, it's changing. But there are also some cons for this combination. And one thing that I was fighting a lot with was changes to interfaces. So basically, you write TensorFlow with a certain version. You write your example. You write your training workflow. You move to a different system or move to a different version of TensorFlow, and nothing is working. And this is really, really frustrating. And I was fighting with that a long time. Also, when it comes to distributed training, the native solution in TensorFlow, especially if you are servicing multiple GPUs on multiple nodes, is a little hacky. So it's not that convenient. You have to take care of a few things that you do not need to take care of, for example, PyTorch distributed, but we will see that in a second. And quite recently, I also stumbled across a few things. It's sometimes a little tricky to install that in virtual environments if you want to do that yourself, because there are several software packages, several dependencies, and if you do not do everything right, then stuff breaks and you don't know why, and you don't find any information about that online. That's frustrating. Good, that's the general overview. So we will basically use that example on the right-hand side, roughly that example later on the slides. But first we will look at distributed training or distributed deep learning. And here I basically repeat the stuff very, very quickly. Yeah? So we currently have two scenarios that come into play in terms of distributed deep learning. One is data parallelism and one is model parallelism. So data parallelism is basically every worker or every GPU has the same model, basically a redundant copy of the same model. And the idea here is basically to split your data and process the data in parallel. So basically here the intention is to get faster. That's the only intention that you want to do. So strong scaling. The other one is model parallelism, and that basically is an issue if your model becomes so big that it does not fit in the GPU memory of a single GPU. So basically you need to split your model up, and different layers or different parts of the model are then trained by different GPUs. So basically here the intention is bigger models. We have seen in PyTorch there are also combinations where you can combine both. So if you have very large models and a lot of data, you want to be fast, but you also want to be able to do that. So basically support bigger models and allow faster training. Good, let's look at some examples. So there are several ways to run distributed deep learning with TensorFlow, and I will basically come back to my little pictures. So one process, multiple GPUs. So basically this is the case for single node with multiple GPUs. And here the go-to solution would be to use TensorFlow's mirrored strategy. So basically mirrored strategy says each of the GPUs has a copy of the model, and then you can use data parallel workflows and split your data across the GPUs. So single process, multiple GPUs, each GPU gets an own copy of the model. Then we have a different case. So we want to use multiple GPUs, and this can be either on one node or also on multiple nodes. So for example, if you want to use 4 nodes and all the 16 GPUs that are within these 4 nodes, then you need to do a small change here. We go from mirrored strategy to multi-worker mirrored strategy. I also linked the documentations if you are interested in that. So basically you have separate processes per GPU, and these can also extend beyond the limit of one node. So the setup is a little bit more tricky. We will see that in a second. So these are the two cases that are TensorFlow native. And then there's a third one, because honestly, this is pretty shitty. Horovod. We can basically use Horovod on top of TensorFlow. And basically what it does is the same thing. We have separate processes, each has its own network. However, this communication, simultaneous backwards propagation and communication of weights of the different networks because they need to stay in sync, is basically not done by TensorFlow, but by Horovod. So the idea here is to wrap this optimizer in TensorFlow and use a distributed optimizer from Horovod. So these are the three go-to ways how to do distributed deep learning in TensorFlow. So as I said, for the simple case, one node, I would recommend this one because it's easy to implement. For the more complex case, I would go for Horovod because it's more stable, it's more performant, and it's not so hacky to implement to set up. Good. Looking at some examples. So we have our very simple case here, and I left some spaces because we will fill that out now. So first of all, we have the loading process that basically stays the same. We load our model, we load our data set, create the data set. Then we have the model creation. I made that here a little bit shorter. I said we have a function, get model, whatever the model is. We compile the model and then we fit it. Basically, we train the model. There are also calls for evaluating. For example, if you do not want to train, but basically just do inference, that's also possible. But here I kept it simple and say we just have the fit. It's training the model. And basically, we need to now extend that with a mirrored strategy. And there are a few steps required to do that. First of all, we need to define the distributed strategy. We need to create and compile the model under the scope of the strategy. And this is pretty simple here in this case, defining the strategy and creating the scope, opening the scope, and then creating and compiling the model. That's it. Nothing special. Good. So basically then TensorFlow will automatically take care of the data sharding process. So basically splitting the data up into parts and then servicing the GPUs with the corresponding slices of data. And also the weight exchanges. So for example, if your model is updated, the model weights are updated, it will keep these copies into sync. Good. So this is a very simple use case for a single node workflow. Now let's look at the more complex one. We have the multi-worker mirrored strategy. So basically we want to use one process per GPU, which also works on a single node, but we have the option to extend that to multiple nodes. And basically what changes here is we have now not the mirrored strategy, but the multi-worker mirrored strategy. However, now it gets complex because we need to do a few more things. Because currently, when we request 4 GPUs, each process sees all 4 GPUs and wants to service all GPUs. So we need to limit the device visibility, that only each process sees its own GPU. Now we can do that from the outside or from the inside. I now decided to do that from the inside. I say we have our local rank. We will see what that means in a bit. But I said, okay, local rank is if we have 4 ranks per node, I say, okay, each gets 0, 1, 2, 3. And I basically do one-to-one assignment and say limit the visibility to this GPU. Now, the second part is if we have a network and there are multiple processes across this network working together, they need to know where to find them. So the connection needs to be clear. So how do they communicate? And this is done using an environment variable, the tfconfig. And this is quite hacky because environment variables are a nice thing in Linux, but encoding JSON into such an environment variable is a very, very bad design decision. But that's how it's done. So basically you create this tfconfig, and typically I do that from the outside. I export that into the environment that is then calling the Python script. And there basically we see that there is some JSON string encoded. Basically the host address with a port, and each process or worker gets his own port. And then you need to specify in the list of these workers, what am I? So each process needs to define that for itself. So we have type worker, index 0 for the first one, For the second one is 1, for the and so on and so on. 2, 3, and if I'm scaling beyond a node, I could have 5, 6, 7, and so on. But each process needs to define this this environment variable for itself in the right manner, in the right manner to work. So this is really hacky. The good part is we tested around a little bit here, and we came up with a very simple script and workflow that it does that for you in the batch job. So you don't need to take care of that by yourself, but it's also possible with a script provided by us. So a little bit more hacky, but still working. Putting that away, going to Horovod. Horovod is a little bit easier to set up. However, it requires some third-party software. So we actually have to import the Horovod package. We have to initialize the Horovod. Data sharding is not done automatically, so we have to take care of that, but it's not that complex. And then we have to wrap the optimizer and unify the model weights. We will go step by step. Importing and initializing is quite easy. You install Horovod, you have this package, you import it, you initialize it with an init call, done. Data sharding is also not that complex. So basically, the only thing that you need to do is shard and say, okay, I have horovod.size and horovod.rank, which will basically be determined automatically by Horovod. So basically, size is the number of workers or GPUs. Rank is my current rank of the process. And each rank will determine that automatically by its own. And then we basically say we have this data set, and I take care of the first part. The next process will take care of the second part, and so on and so on. Good. Then we have the model creation and model compilation. And here, this part comes into play, wrapping the optimizer. And basically, the only thing that we do is we use the regular TensorFlow Keras Adam optimizer in this case, and wrap it with a distributed optimizer, and then feed it into the model compile. That's the only thing that you need to do in this case. Good. And then there's one step missing, and this is model weights. So basically, each of the GPUs has its own copy of the network. And if you don't specify anything else, then these weights are initialized in a random way. So the starting point of the training is completely random and also different on each of the copies. And this is not what you want. You want a unified starting point and then process your data in parallel and then sync again. So the syncing in the workflow is done with a distributed optimizer, so this is okay, but the starting point is not okay. So we need to start at the same point for each of the copies. And this is done in the model fit using a special callback. You can pass callbacks there. And this callback is broadcast global variables callback. And this basically does exactly that thing. It broadcasts the weights from rank 0 to all the other copies that we have a unified starting point. And that's it. It looks a little bit nicer, a little bit cleaner compared to the hacky JSON environment variable workflow. And in tests, we have seen that it's also more performant. Good. Now I will shortly talk about the different options how to execute stuff on our system. We basically have two ways, containers and environment variables. The good part about containers is it encapsulates all the software and dependencies and stuff like that that you need for this software package. For example, if you have the TensorFlow container, it has TensorFlow, but also all CUDA, CUDA, and all the dependencies that you need for TensorFlow. And it's basically prepared by NVIDIA, and we ship it here in our cluster and basically create an Aptainer image out of that, and that works out of the box. That's really nice. There are also some pros and cons here, of course. The good part is about reproducibility. So as soon as you create your scripts with that container, you can use the same environment to execute it. You have really reproducible experiments, and you can also do that in teams, for example. If you say, I use that container, then your colleague can do the same thing with the container, has the same software environment, no differences. The other advantage is we have less pressure on the file system, and that is a little bit caused by virtual environments. So if every user installs its own virtual environment, thousands of files, a lot of data volume, so a lot of copies and potentially redundant copies. So we want to keep that low here, less pressure on the file system. We have one software environment, predefined, optimized, that you can use out of the box. The drawback is once the container is built, it's hard to change it. There are some ways, but in principle, our container images are read-only. And of course, that is a challenge if some packages are missing. But there are ways around that. For example, you can install missing packages in your user environment, and then basically both is available in the container environment as well as the user environment. We did that here yesterday already with a few packages. Good, virtual environments, there are different solutions for that. There's the classical pip way, so Python virtual environment. There's the Conda Forge way. Please don't use Anaconda on our systems anymore. There are some license changes in Anaconda that basically prevent us from using that here, so we blocked that. So Conda Forge is the way to go, basically pretty similar, but with open source packages, no licenses, so that's the way to go. The good part is it can be used as well as on your desktop system. It's highly flexible, so if you need a very specific version that we don't have on our cluster, if you need other packages, you can basically install that and create your custom environment. That is the good part, but as I said, if everyone has its own installation, we have sometimes 35K or more files. That's tricky. So high pressure on the cluster, on the file system, on the network. Less reproducibility. So if your colleague has your virtual environment with different versions and you have one with different versions, then the classical thing happens, but it works on my machine. It's not really helpful. So better go for something that is more reproducible in terms of teamwork. And of course, for us, it's hard to provide support because we don't know how your virtual environment is set up. So if you have any problems or questions, it's hard to give you support and know what's actually happening because there are so many things that can go wrong in setting up a virtual environment. Good, here just a few more information about containers. I think we don't need to go into too much detail. There are typical container frameworks like Docker, Shifter, Aptainer. Due to constraints, we only use Aptainer here. But there are also ways to convert a Docker container. So if you have some specific software you want to execute and it's in a Docker container, you can transform that into an Aptainer container out of the box and run on our system. I will not go too much into detail here. There are a few containers available on our system. So we have predefined containers for PyTorch, for TensorFlow, and we have what's called Data Science Notebook. It basically holds packages for scikit-learn and different other data science packages. So it's quite a long list. I didn't put that here, but the most important part, TensorFlow and PyTorch, is available. There are also options for user containers. So if you bring your own container, that's also possible. And if you think that a very, very important container is missing that might be useful for a lot of people, then please contact us. Then we will have a look and potentially provide this centralized container image as well. Good, so putting it all together. So we have different aspects now. We have our Slurm and batch scripts. We have here in this case TensorFlow, containers. On the other part, we have PyTorch and containers. And our scripts. And the question is, how can we now put things together? So what I have is, so I said demo. Let's have a look. We have some examples, and we also provide that on the website later on. So basically, I have examples for PyTorch. I have examples for TensorFlow. I have some examples that are relevant tomorrow in terms of Slurm and beyond. But basically here, let's have a look. Where's my mouse? Here we have, for example, pretty simple examples, CIFAR classification, single GPU, multi-GPU, and here I have basically the Python scripts for Horovod and regular native TensorFlow and different subnet scripts. Yeah? And here we have different cases like container using Horovod, container single node that basically uses the mirrored strategy. We have the regular container that's basically using the multi-mirrored strategy. And then we have venv. We don't use that. We will not use that because I don't have a virtual environment in place right now. Yeah? And we have some supporting scripts like limit the GPU visibility, set environment variables that are then also available in the container, and an execution wrapper, and the script that basically creates this tf-config for you, which is quite neat. Good. So let's have a look at a very simple case here. Yeah. So we have our Slurm flex. We have seen that before. We want to use GPUs, one node. We have here two processes and two GPUs, so one-to-one mapping. Do we have one-to-one mapping here? Oh, that's wrong. That should be one. Okay, so basically in terms of software, we load the container, the TensorFlow container. Yeah? This is just verbose output that you see that also in the job script later on. We do have some more verbose output and set a few parameters. This is basically just for multi-threading, communication, and so on. This is optimization stuff to make it a little bit faster in terms of communication and debugging messages. And then we have basically our Python call, and this is wrapped inside the container. Yeah? So first of all, we set a few variables that are required. And this is the mirrored strategy that does not use this JSON stuff. And here we simply say we want to execute this TensorFlow image. Here there are a few flags like we want to make the NVIDIA GPUs and stuff like that available within the container. And then we say Python train model Py, and here we say strategy mirrored. No? And basically that will call this script. It's also not very huge, so it's like 120 lines of code or something. We can, I don't know if it makes sense to look at that, maybe shortly. So basically, we have a main function. Yeah? Here we also do some seeding stuff to make sure that every process gets the same seeds. We pass command line arguments. We define the strategy with, in this case, is a multi-mirrored strategy, mirrored strategy only. Load our data sets, and there are functions for those. Yeah? And then we use the strategy scope, define our model, which in this case is a ResNet model, define the optimizer, compile the model, and then later on we fit. Yeah? I will not go in the details right now, but there are functions for that. You can have a look at that. You can download the package, the zip file with all the examples and have a look and use that as a base for yourself. Yeah? But this is basically a very simple example of executing a container, the Python script in the container, and before we need to set a few variables. That's it. Yeah? So this is putting it all together. So this single node case, now it gets a little bit more tricky. Multi-node case. Yeah? So basically we have here still a single node, but we have two processes. You can also run this multi-worker mirrored strategy on a single node with two processes. This is a very simple example, two GPUs, two workers, same container, same settings. And now it gets a little bit more tricky. Yeah? We do not use stuff like torch run to start multiple processes, but we use our MPI, so basically srun, to create multiple processes. And these processes all do similar things. Yeah? They limit the GPU visibility, set certain variables, and then instead of executing the Python code directly, we have a wrapper script. And why do we have the wrapper script? Because it's a little tricky to put the JSON stuff in there. Yeah, so basically the wrapper script only does the tf-config, exporting the tf-config for the current process, and then calling the Python. That's the only thing that the wrapper does. Yeah? So nothing complex. Okay, good. So these examples will be online. Yeah, if they are already online, perfect. So you can have a look, and if you have any questions, just let us know. Yeah. Just again, a reminder, multiple processes are required to do distributed training. Yeah? How they are created depends. Yeah? So here in these examples, we use srun, so basically MPI, but there are also options like torch run or classical Python multiprocessing to spawn processes. Yeah? What you prefer depends a little bit on your scenario and depends a little bit on the environment that you execute in. Yeah? For example, classical Python multiprocessing will only spawn processes within a single node. And you need some combination with srun in order to make that happen. That's why it might be easier to directly use srun, but it depends. Good, thank you.